Aryabhata.
Aryabhata or Aryabhata I was the first in the line of great mathematician-astronomers from the classical age of Indian mathematics and Indian astronomy. His works include the Aryabhatiya and the Arya-siddhanta. The works of Aryabhata dealt with mainly mathematics and astronomy.
Biography. Name.
While there is a tendency to misspell his name as Aryabhata by analogy with other names having the bhata suffix, his name is properly spelled Aryabhata. Every astronomical text spells his name thus, including Brahmagupta's references to him in more than 100 places by name. Furthermore, in most instances Aryabhata does not fit the meter either.
Time and place of birth.
Aryabhata mentions in the Aryabhatiya that it was composed 3,600 years into the Kali Yuga, when he was 23 years old. This corresponds to 499 CE, and implies that he was born in 476. Aryabhata provides no information about his place of birth. The only information comes from Bhaskara I, who describes Aryabhata as Asmaka, one belonging to the Asmaka country. During the Buddha's time, a branch of the Asmaka people settled in the region between the Narmada and Godavari rivers in central India. Aryabhata is believed to have been born there.
Other hypotheses.
It has been claimed that the Asmaka, Sanskrit for stone where Aryabhata originated, may be the present-day Kadangala, which was the historical capital city of Thiruvankaram Kulam of ancient Kerala. This is based on the belief that Kotanala was earlier known as Kotamkallala, city of hard stones. However, old records show that the city was actually Kotamkalla, city of strict governance. Similarly, the fact that several commentaries on the Aryabhatiya have come from Kerala has been used to suggest that it was Aryabhata's main place of life and activity. However, many commentaries have come from outside Kerala, and the Arya-siddhanta was completely unknown in Kerala. Aryabhata mentions Lanka on several occasions in the Aryabhatiya, but his Lanka is an abstraction, standing for a point on the equator at the same longitude as his Ujjaini.
Education.
It is fairly certain that, at some point, he went to Kisumapura for advanced studies and lived there for some time. Both Hindu and Buddhist tradition, as well as Bhaskara I, CE 629, identify Kisumapura as Pataliputra, modern Patna. A verse mentions that Aryabhata was the head of an institution, Kulapa, at Kisumapura, and, because the University of Nalanda was in Pataliputra at the time and had an astronomical observatory, it is speculated that Aryabhata might have been the head of the Nalanda University as well. Aryabhata is also reputed to have set up an observatory at the Sun Temple in Tarragona, Bihar.
Works.
Aryabhata is the author of several treatises on mathematics and astronomy, some of which are lost. His major work, Aryabhatiya, a compendium of mathematics and astronomy, was extensively referred to in the Indian mathematical literature and has survived to modern times. The mathematical part of the Aryabhatiya covers arithmetic, algebra, plane trigonometry, and spherical trigonometry. It also contains continued fractions, quadratic equations, sums of power series, and a table of signs. The Arya-siddhanta, a lost work on astronomical computations, is known through the writings of Aryabhata's contemporary, Varamihira, and later mathematicians and commentators, including Brahmagupta and Bhaskara I. This work appears to be based on the older Arya-siddhanta and uses the midnight day reckoning, as opposed to sunrise in Aryabhatiya. It also contained a description of several astronomical instruments, the gnomon, Shankhu yantra, a shadow instrument, Chhia yantra, possibly angle measuring devices, semicircular and circular, Dana yantra/chakra yantra, a cylindrical stick yasti yantra, an umbrella-shaped device called the chatra yantra, and water clocks of at least two types, bow-shaped and cylindrical. A third text, which may have survived in the Arabic translation, is Al-Ntf or Al-Nanf. It claims that it is a translation by Aryabhata, but the Sanskrit name of this work is not known. probably dating from the 9th century. It is mentioned by the Persian scholar and chronicler of India, Abu Rayhan al-Biruni.
Aryabhatiya.
Direct details of Aryabhata's work are known only from the Aryabhatiya. The name Aryabhata is due to later commentators. Aryabhata himself may not have given it a name. His disciple Bhaskara I calls it Ashmakatantra, or the treatise from the Ashmarka. It is also occasionally referred to as Aryashitta's Ashta, literally, Aryabhata's 108, because there are 108 verses in the text. It is written in the very terse style typical of sutra literature, in which each line is an aid to memory for a complex system. Thus, the explication of meaning is due to commentators. The text consists of the 108 verses and 13 introductory verses, and is divided into 4 padas or chapters. Jitikapada, 13 verses, large units of time, Kalpa, Manvantara, and Yuga, which present a cosmology different from earlier texts such as Lugaba's Vedanga Jyotisha, c. 1st century BCE. There is also a table of signs, given in a single verse. The duration of the planetary revolutions during a Mahayuga is given as 4.32 million years. Ganitapada, 33 verses, covering mensuration, Kshatrivivahara, arithmetic and geometric progressions, gnomon/shadows, Shanku Chhia, simple, quadratic, simultaneous, and indeterminate equations. Kalakapada, 25 verses, different units of time and a method for determining the positions of planets for a given day, calculations concerning the intercalary month, Adhikam Asa, Kshatrithis, and a 7-day week with names for the days of week. Galapada, 50 verses, geometric trigonometric aspects of the celestial sphere, features of the ecliptic, celestial equator, node, shape of the Earth, cause of day and night, rising of zodiacal signs on horizon, etc. In addition, some versions cite a few colophons added at the end, extolling the virtues of the work, etc. The Aryabhata presented a number of innovations in mathematics and astronomy in verse form, which were influential for many centuries. The extreme brevity of the text was elaborated in commentaries by his disciple Bhaskara I, Bhashya, c. 600 CE, and by Nilakantha Somarauji in his Aryabhata Bhāsya, 1465 CE.
Mathematics. Place value system and zero.
The place values system, first seen in the 3rd century Bakhshali manuscript, was clearly in place in his work. While he did not use a symbol for zero, the French mathematician Georges Ifra argues that knowledge of zero was implicit in Aryabhata's place value system as a placeholder for the powers of 10 with null coefficients. However, Aryabhata did not use the Brahmi numerals. Continuing the Sanskritic tradition from Vedic times, he used letters of the alphabet to denote numbers, expressing quantities, such as the table of signs in a mnemonic form.
Approximation of P.
Aryabhata worked on the approximation for pi, and may have come to the conclusion that is irrational. In the second part of the Āryabhatiya, Ganitapada 10, he writes, "This implies that the ratio of the circumference to the diameter is 4 plus 100 closing round bracket times 8 plus 62,000, / 20,000 equals 62,832 20,000ths equals 3.1416, which is accurate to 5 significant figures." It is speculated that Aryabhata used the word asana, approaching, to mean that not only is this an approximation but that the value is incommensurable, or irrational. If this is correct, it is quite a sophisticated insight, because the irrationality of pi was proved in Europe only in 1761 by Lambert. After Aryabhata was translated into Arabic, c. 820 CE, this approximation was mentioned in Al-Khwarizmi's book on algebra.
Trigonometry.
In Ganitapada 6, Aryabhata gives the area of a triangle as. That translates to, for a triangle, the result of a perpendicular with the half side is the area. Aryabhata discussed the concept of sign in his work by the name of Āryabhatiya, which literally means half-chord. For simplicity, people started calling it Ya. When Arabic writers translated his works from Sanskrit into Arabic, they referred it as Jiba. However, in Arabic writings, vowels are omitted, and it was abbreviated as JB. Later writers substituted it with Jayb, meaning pocket, or fold, in a garment. In Arabic, Jiba is a meaningless word. Later in the 12th century, when Rado of Cremona translated these writings from Arabic into Latin, he replaced the Arabic Jayb with its Latin counterpart, sinus, which means cove, or bay. Thence comes the English sign. Alphabetic code has been used by him to define a set of increments. If we use Aryabhata's table and calculate the value of sin, 30, corresponding to HASJHA, which is 1719 3438 equals 0.5. The value is correct. His alphabetic code is commonly known as the Aryabhata cipher.
Indeterminate equations.
A problem of great interest to Indian mathematicians since ancient times has been to find integer solutions to equations that have the form x plus by equals c, a topic that has come to be known as Diophantine equations. This is an example from Bhaskara's commentary on Aryabhatiya. That is, find n equals 8x plus 5 equals 9y plus 4 equals 7z plus 1. It turns out that the smallest value for n is 85. In general, Diophantine equations, such as this, can be notoriously difficult. They were discussed extensively in ancient Vedic text Sulbas Sutras, whose more ancient parts might date to 800 BCE. Aryabhata's method of solving such problems is called the Kutaka, Kuttk, method. Kutaka means pulverizing, or breaking into small pieces, and the method involves a recursive algorithm for writing the original factors in smaller numbers. Today this algorithm, elaborated by Bhaskara in 621 CE, is the standard method for solving first-order Diophantine equations and is often referred to as the Aryabhata algorithm. The Diophantine equations are of interest in cryptology, and the RSA Conference, 2006, focused on the Kutaka method and earlier work in the Sulba Sutras.
Algebra.
In Aryabhatiya, Aryabhata provided elegant results for the summation of series of squares and cubes. And
Astronomy.
Aryabhata's system of astronomy was called the Āryaka system, in which days are reckoned from Āday, dawn at Lanka or equator. Some of his later writings on astronomy, which apparently proposed a second model, or Āryabhaṭīya, midnight, are lost but can be partly reconstructed from the discussion in Brahmagupta's Kandak Adhyaka. In some texts, he seems to ascribe the apparent motions of the heavens to the Earth's rotation. He may have believed that the planet's orbits as elliptical rather than circular.
Motions of the solar system.
Aryabhata correctly insisted that the Earth rotates about its axis daily, and that the apparent movement of the stars is a relative motion caused by the rotation of the Earth, contrary to the then prevailing view, that the sky rotated. This is indicated in the first chapter of the Aryabhatiya, where he gives the number of rotations of the Earth in a yuga, and made more explicit in his Gola chapter. Aryabhata described a geocentric model of the solar system, in which the Sun and Moon are each carried by epicycles. They in turn revolve around the Earth. In this model, which is also found in the Arya-siddhanta, c. 425, the motions of the planets are each governed by two epicycles, a smaller Manda, slow, and a larger Sira, fast. The order of the planets in terms of distance from Earth is taken as the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and the asterisms. The positions and periods of the planets was calculated relative to uniformly moving points. In the case of Mercury and Venus, they move around the Earth at the same mean speed as the Sun. In the case of Mars, Jupiter, and Saturn, they move around the Earth at specific speeds, representing each planet's motion through the zodiac. Most historians of astronomy consider that this two-epicycle model reflects elements of pre-Ptolemaic Greek astronomy. Another element in Aryabhati's model, the Siraka, the basic planetary period in relation to the Sun, is seen by some historians as a sign of an underlying heliocentric model.
Eclipses.
Solar and lunar eclipses were scientifically explained by Aryabhata. He states that the moon and planets shine by reflected sunlight. Instead of the prevailing cosmogony in which eclipses were caused by pseudo-planetary demons Rahu and Ketu, he explains eclipses in terms of shadows cast by and falling on Earth. These will only occur when the Earth-Moon orbital plane intersects the Earth-Sun orbital plane, at points called lunar nodes. Thus, the lunar eclipse occurs when the Moon enters into the Earth's shadow, verse Gola 37. He discusses at length the size and extent of the Earth's shadow, verses Gola 38-48, and then provides the computation and the size of the eclipsed part during an eclipse. Later Indian astronomers improved on the calculations, but Aryabhata's methods provided the core. His computational paradigm was so accurate that 18th-century scientist Guillaume Le Gentil, during a visit to Pondicherry, India, found the Indian computations of the duration of the lunar eclipse of August 30, 1765 to be short by 41 seconds, whereas his charts, by Tobias Mayer, 1752, were long by 68 seconds.
Sidereal periods.
Considered in modern English units of time, Aryabhata calculated the sidereal rotation, the rotation of the Earth referencing the fixed stars, as 23 hours, 56 minutes, and 4.1 seconds. The modern value is 2356.4.091. Similarly, his value for the length of the sidereal year at 365 days, 6 hours, 12 minutes, and 30 seconds, 365.25858 days, is an error of 3 minutes and 20 seconds over the length of a year, 365.25636 days.
Heliocentrism.
As mentioned, Aryabhata advocated an astronomical model in which the Earth turns on its own axis. His model also gave corrections, the Sigra anomaly, for the speeds of the planets in the sky in terms of the mean speed of the Sun. Thus, it has been suggested that Aryabhata's calculations were based on an underlying heliocentric model, in which the planets orbit the Sun, though this has been rebutted. It has also been suggested that aspects of Aryabhata's system may have been derived from an earlier, likely pre-Ptolemaic Greek, heliocentric model of which Indian astronomers were unaware, though the evidence is scant. The general consensus is that a synodic anomaly, depending on the position of the Sun, does not imply a physically heliocentric orbit, such corrections being also present in late Babylonian astronomical texts, and that Aryabhata's system was not explicitly heliocentric.
Legacy.
Aryabhata's work was of great influence in the Indian astronomical tradition and influenced several neighboring cultures through translations. The Arabic translation during the Islamic Golden Age, c. 820 CE, was particularly influential. Some of his results are cited by al-Khwarizmi, and in the 10th century al-Biruni stated that Aryabhata's followers believed that the Earth rotated on its axis. His definitions of sine, cosine, kauya, basine, utkramya, and inversine, otkramya, influenced the birth of trigonometry. He was also the first to specify sine and versine, 1. Cos x, tables, in 3.75 deg intervals from 0 deg to 90 deg, to an accuracy of 4 decimal places. In fact, modern names sine and cosine are mistranscriptions of the words ya and kauya as introduced by Aryabhata. As mentioned, they were translated as jiba and kijiba in Arabic and then misunderstood by Gerard of Cremona while translating an Arabic geometry text to Latin. He assumed that jiba was the Arabic word jaib, which means fold in a garment, L. Sinus, c. 1150. Aryabhata's astronomical calculation methods were also very influential. Along with the trigonometric tables, They came to be widely used in the Islamic world and used to compute many Arabic astronomical tables, zijs. In particular, the astronomical tables in the work of the Arabic Spain scientist al-Zarqali, 11th century, were translated into Latin as the Tables of Toledo, 12th century, and remained the most accurate ephemeris used in Europe for centuries. Calendric calculations devised by Aryabhata and his followers have been in continuous use in India for the practical purposes of fixing the Panchandram, the Hindu calendar. In the Islamic world, they formed the basis of the Jalali calendar introduced in 1073 CE by a group of astronomers including Omar Khayyam, versions of which, modified in 1925, are the national calendars in use in Iran and Afghanistan today. The dates of the Jalali calendar are based on actual solar transit, as in Aryabhata and Arya-siddhanta calendars. This type of calendar requires an ephemeris for calculating dates. Although dates were difficult to compute, seasonal errors were less in the Jalali calendar than in the Gregorian calendar. Aryabhata Knowledge University, AKU, Patna has been established by Government of Bihar for the development and management of educational infrastructure related to technical, medical, management and allied professional education in his honor. The university is governed by Bihar State University Act 2008. India's first satellite Aryabhata and the lunar crater Aryabhata are named in his honor. An institute for conducting research in astronomy, astrophysics and atmospheric sciences is the Aryabhata Research Institute of Observational Sciences, ARIS, near Nainital, India. The inter-school Aryabhata maths competition is also named after him, as is Bacillus aryabhata, a species of bacteria discovered by ISRO scientists in 2009.